I would like to start with this webinar today on layer of protection analysis and engineering tools. The layer protection analysis in relationship to the IEC 61511 standard. For those of you who have attended our webinars before, you will know that the audio is coming over your PC speakers. The webinars are set up such that there is only one-way audio. So if you have any questions or comments, you can use the Q&A section at the top of your live meeting screen. There is the menu that indicates the Q&A. That's where you can add any questions, and I will try to answer those questions as we go along through this webinar. There's also going to be a recording of this webinar, which will be made available on the Exid website at the end of the webinar. So let's get started today with this webinar on IEC 61511, layer of protection analysis and engineering tools. My name is Yuan van Beurden. I'm the Director of Engineering at Exid. I support Exid's end-user services. I support our manufacturer services, and I also support our certification activities. I'm overall responsible for the development, maintenance, and certification of the Excelencia integrated safety lifecycle tool, and I perform a bunch of different things, ranging from IEC 61508 development support to IEC 61511 compliance support. I do functional safety assessment audits, variety of reliability analysis, SIL selection, SIL verifications, and I'm an Exid and ISA instructor. I assume most of you are familiar with Exid. Just as a quick reminder, Exid, we're a knowledge company. We pride ourselves on a concept of verifiable functional safety. We have several offices around the world, for example in Calgary, Canada, and the Philadelphia area here in the US, Munich, Germany. We have an office in Geneva, Switzerland, in South Africa, and we're actually also just opened up an official office in Mexico, and we're working on Asia Pacific, Singapore to be precise, to be a legal subsidiary of Exid. And in addition to that, we have various service centers, smaller locations from which some of our partners and engineers will assist customers. So that is a little bit of background on Exid. We're functional safety, cybersecurity. Those are our key tasks. We apply that to a variety of industries: process industry, machinery industry, nuclear industry, automotive industry. But today we'll focus primarily on the process industry. So there's a lot of talk about safety. What is safety? You may be familiar with some of these terms that you see here: SIL, safety integrity level; S84, IEC 61511; LOPA, layer of protection analysis; SIF, safety instrument function; IEC 61508. And at least at the end of this webinar, I hope there's a little bit of clarity on at least the IEC 61511 S84 standards with relation to layer of protection analysis. The key standards to look at when we talk about functional safety are the IEC 61508 standard and the IEC 61511 standard. The IEC 61508 standard is an umbrella standard. It applies to all industries, and it addresses functional safety of electrical, electronic, and programmable electronic safety-related systems. as I mentioned, it applies to all industries, and it also is set up such that industry-specific standards can be derived from it. So there is a nuclear industry sector, a process industry sector standard, there is a machinery industry sector standard, there's going to be an automotive industry sector standard as well. In the process industry, IEC 61511 is the international derivative. In the US, there is the ANSI ISA 840001-2004, which is a variation of IEC 61511 in that it has some explanatory text in addition to a grandfather clause. One of the key things to remember, these are performance-based standards, they're not prescriptive, meaning that you can do whatever you want as long as you can demonstrate that you meet your performance criteria. At the same time, a negative is that there are no prescriptive rules telling you what to do. Another aspect is that these functional safety standards introduce something that we call the safety life cycle, a rigorous process that addresses all the steps in the functional safety in the life of a unit to ensure that functional safety is achieved and maintained. Third aspect here, functional safety management governs the activities associated with equipment and process safety as it involves correct functioning of specific safety systems. Functional safety management is also a key aspect in these functional safety standards. An alternate picture here, IEC 61508 is the umbrella standard, applies to all industries, and then there are some industry sector specific derivative standards like IEC 61513, IEC 62061, and IEC 61511, which is the process industry sector standard. Also ISA 840001-2004, main difference, the grandfather clause in the US version of the standard. So let's look at the 61511 standard, and it's definitely becoming a standard of choice for many companies that are doing work in the process industry that deal with functional safety issues. We've done some surveys within Exid over the first couple of years in the new millennium. In 2001, 2002, up to 2005, we basically asked the question to a variety of customer or potential customers, people in the industry, are you using or planning on using IEC 61511 or IEC 61508? And what you can see here is that in 2001, it's basically not adopted. In 2002, more people are becoming aware. In 2003, the year that IEC 61511 was released, there's a huge jump, and then in 04 and 05, there's almost an asymptotically approximation to the 100% of people that are implementing it. Industries that are included: oil and gas production, refining, chemical, power, pharmaceutical, and where end users are more and more using this 61511 standard, or the ISA 84 standard, we also see that the demand for 61508 certified equipment is increasing, as that is one of the aspects of 61511. You need to either use equipment that you have a significant documented history, proven and use on, or you use equipment that has been assessed for 61508. So the two go hand in hand. Many multinational companies have their internal safety groups that are implementing these standards on a global basis. In the US, OSHA requires, as part of your process safety management, that you use good engineering practices. It doesn't really tell you what that means, except there is a letter from OSHA to ISA indicating that ISA 84.0001 is a good example of good engineering practices. So though 61511 may be mandatory over in Europe, it's optional here in the US. You need to do good engineering practices, but this is an example of good engineering practices. In the last couple of years, there have been a couple of situations where OSHA inspectors went to sites where there was an incident, and they have fined some of these companies because they weren't compliant to the S84 standard. So there is some indication. Obviously, it's not a law here in the U.S., but there is some indication that OSHA is definitely using S84 as the guideline to which everybody is held when it comes to compliance if something goes wrong, etc. Some critical issues in 6.15.11. It defines user project requirement very well, talks about the safety life cycle. It addresses the software development process for limited variability languages, the requirements that you need to meet. Limited variability languages are languages like function blocks, structured text, sequential function charts, ladder logic, basically the IEC 61131-3 languages, if I remember correctly. It also addresses fault tolerance, redundancy requirements. It does talk about integrating control and safety. There are some restrictions if the control system is the initiating event. It talks about disproven use or 6.15.08 compliance for all equipment. And then finally, it requires the management of the requirements within a project. So those are some things that arguably are all part of functional safety management, and good functional safety management has a well-defined life cycle approach for implementation of 6.15.11, but that could be a little bit tricky when you start out with this stuff. As an idea of what this life cycle looks like, this functional safety life cycle, we basically start up at the beginning when we have a concept. We do a hazard identification through a PHA or HAZUP. What can go wrong is the question that we're trying to answer. This is followed by the risk analysis and SIL selection. How bad can it be? For example, we could do a layer of protection analysis, and of course that's the topic of today, so we will be talking more about that. Followed by safety requirement specification, where we basically document these are the risks, these are the hazards that we have identified. These are the functions that need to be implemented to protect against that. And then in the next step, we are doing the SIL verification, the conceptual design, where we try to come up with something that will protect against this hazard with a specific level of risk reduction. How reliable is it is the question. And then finally, the sustain phase. Once we are in operation, we need to make sure that we keep our safety. How do we keep everything safe? The objective of this functional safety life cycle is to reduce risk to a tolerable level. So we want to eventually to be able to walk around a specific plant and say, well, there is some risk. Everything that we do has risk, but this risk is at a tolerable level. We can live with that, and those tolerable risk levels are typically specified on a corporate level. The three parts in IEC 61511, part 1, 2, and 3. Part 1 is the normative part. That's what the index N stands for, normative. If you are looking for compliance with IEC 61511, this is the part that you need to look at. The scope is a system approach, complete loop, safety life cycle, management of functional safety, probabilistic target failure measurement, configuration of safety instrument functions and application software. That's all addressed in this first part, basically the safety requirements. Then part 2 is informative. Part 3 is informative. Part 2 gives you guidance on how to be compliant with part 1, and part 3 gives guidelines on risk evaluation. Basically, a number of different methods to determine your target safety integrity level and the risk reduction, basically, that you need to achieve. The layer of protection analysis that we will be talking about today is also explained in this part 3 of 61511. Now keep in mind, this is informative, so anything that's stated in there is just for information. It's not required that you do it this way. There are a bunch of different ways to do SIL selection or SIL determination, but it at least gives you some idea of how to implement it. So what is LOPA? What is layer of protection analysis? Well, LOPA, layer of protection analysis, I think most of us are familiar with that abbreviation. It is a form of risk assessment often used to determine the safety integrity level targets based on an initiating event frequency, a consequence severity, likelihood of failure of independent protection layers, and a specific risk scenario. It is semi-quantitative or quantitative tool that builds on the qualitative hazard identification from the process hazard analysis, typically your hazard and probability study. And it allows us to clearly take credit for different layers that have been implemented, or different protections that have been implemented when it comes to determining how much risk reduction we need. There is one comment here. I'm not sure if everybody can see that. IEC 61511 uses the term allocation of safety layers, not layer of protection analysis. Just a clarification there from Mr. Joseph. 61511 uses the term allocation of safety layers, not layer of protection analysis. Layer of protection analysis is just the common terminology that this method has received through, for example, the work that the ASCG CCPS group has done over the last couple of years. One of the I would almost say Bibles on this work was written by the CCPS group, and it's obviously called layer protection analysis. So this is the question: what is layer protection analysis? So apologize for that. So let's look at this. We have a normal process and a process variable, let's say pressure, and that pressure is within a certain operating limit, and that is just part of our normal process design. The pressure, if it goes above a certain trip point, we'll have process control trying to keep that pressure within the original design limits. If that doesn't work, there may be an alarm, and the alarm initiated to an operator intervention. If the operator is not successful, pressure keeps rising, then we may have a trip initiated by a safety instrumented system. And if that is not successful, then arguably we could have an incident. We could, for example, have a relief valve or a rupture disc that helps us reducing the pressure. If that layer is not successful, then we could have loss of containment. We may have some passive protection, for example, a dike, or a planned emergency response, or a community emergency response. So there are different, within a typical process unit, there are different layers built into that process. One of the things that people ask quite a bit is, can we combine control and safety? And the answer is yes, you could, but from this picture, it's very clear to see that if you combine control and safety, that you're basically losing one layer of protection. So the combination of the two needs to be, you need to make sure that that is of the same level of risk reduction that the two separate layers were, and also need to make sure that the process control layer is not the initiating event. But this simple diagram here shows you the different levels, different protection layers that we could have for a specific hazard. In this case, the high pressure event. The protection measures is a little bit like this Swiss cheese diagram. Hazards are restrained or contained by multiple protection barriers. Barriers may have weaknesses or holes, and when those holes align, then the hazard is released, resulting in the potential for harm. The barriers could be physical engineered containment or behavior controls, depending on people. And again, the holes can be latent, inbuilt problems, actively opened by failure of equipment or people. And then this picture is basically indicating if all those holes align, then you could have a problem. So what does layer of protection analysis? It provides the analyst with a method to evaluate the risk of a selected accident scenario and identify additional risk reduction opportunities. And it's a very structured method so that it's easy to reproduce, easy to follow by others that may be reviewing the work that you've done. Each LOPA scenario is limited to a single cause-consequence pair. For those of you who listen in to the PHA webinar that I did last week, that was the key definition of a hazard, the combination of a single cause-consequence. How can you look at this? Well, let's say the big arrow on the left is the initiating event with a certain level of risk. We have protection layers, and those protection layers reduce the risk. So we have protection layer 1, protection layer 2, protection layer 3, and we end up with a with a event frequency that is much lower with a lower level of risk associated with. So these three protection layers basically reduce that initial big arrow to the smaller, narrower arrow. And also from a event-free type diagram, we start out, and this is the diagram at the bottom, we start out with an initiating event. The initiating event could have, well, goes to the first protection layer. If that first protection layer is successful, then we have a safe outcome. If the first protection layer fails, then we go on to the next protection layer. If that one fails, we go on to the third protection layer, and if that one fails, we end up with the actual accident. So there are a couple of areas here where protection layers can be successful, and we end up with an undesired but tolerable outcome. We end up with risks that are much lower than the initial risk, something that we could tolerate or basically live with. If you look at the layers of protection from the Swiss cheese perspective, the one on the left basically represents the Swiss cheese with a bunch of holes, which is pretty useless when it comes to protection, from a protection perspective. And that would equate to basically a probability of failure equaling 1, meaning it will fail every 100 out of 100 times, and it will be an equivalent of, let's say, a SIL 0. So that gives you a little bit of a feeling of orders of risk reduction that you would claim with a layer of protection. If you have a layer of protection, this is the second picture that has a couple of holes, 10 out of, let's say, 100. A probability of failure will be 0.1. It's relatively weak protection layer, and will be equivalent of risk reduction factor in the order of SIL 1, then an almost perfect but still imperfect protection layer where you only have one hole out of 100, equivalent to risk reduction in the SIL 2 range, TFD of 0.01, and then all the way to the right you have your perfect protection layer, something with a probability of failure equaling to 0. There are no holes, and basically the amount of risk reduction that you achieve will be equivalent to a SIL level that is equal to infinity. Now, all the way to perfect, that is probably something that is fairly uncommon. The Swiss cheese on the left is basically a useless protection layer. The imperfect, you could say it's a Gouda cheese. There may be a hole here or there. The Dutch cheese is better than the Swiss cheese, whatever you want to go at with this. But of course, the more holes that there are in a specific protection layer, the more likely it is that the different holes line up and that you eventually have an incident. So the more barriers, the less probable that the holes will coincide to pass the hazard. If the barriers have holes in the same place, for example, a common cause failure, then the probability of the incident alignment is higher. So that is something to keep into consideration if the different layers have something in common. But for now, let's assume that everything is independent. So when should we use layer of protection analysis? Well, typically The initial sill selection or sill determination is done by means of a risk graph or hazard matrix, a quick qualitative hazard evaluation. You end up with target sills, and for everything that at that point drops off as being a sill 0, basically that's where all your worries end. For things that end up with a higher level of risk reduction required, as maybe sill 2 or sill 3, you may want to look into a more detailed analysis by means of a layer protection analysis. So criticality is an issue. Things with severe consequence, regardless of the likelihood, then things with high risk, a high product of consequence and likelihood, and then also things that are very complex. If you try to estimate a likelihood for a very complex event, that's going to be very tough. But if you break that complex event up into simpler, smaller events, then you can probably relatively easy estimate the occurrence of the smaller events, and with that come up with the complex event frequency. So how does it work? We'll typically start out with an estimation of consequence and severity. We develop our scenarios. We identify initiating event frequencies. We identify related independent protection layers. We determine scenario frequency, and we make risk decisions. Also, to keep in mind, this fault propagation modeling, typically when we talk about an overpressure event, that is not necessarily just a control system failing. There could be several layers in place. Again, this falls into the same category as the complexity that I mentioned earlier. There are different steps that you have to go through, different slices of cheese, basically. Control system failing, operator does not respond properly, a mechanical relief valve failed. Then we have an overpressure event. Through this fault propagation modeling, we will be able to adequately estimate what the overpressure event frequency is, what the risks are associated with this specific hazard, rather than trying to come up with one overall overpressure event frequency, taking all these things into account. So the layer protection analysis is a variation of event tree. There are more rules. We will be talking about those rules in just a bit. We are only considering two outcomes. We either have an accident or no. So the protection layer is successful or it's not successful. If it is successful, the outcome is not going to happen. The math that is associated with it, with the layer protection analysis, is very simple multiplication math. You start out with an initiating event and you multiply that with the probability of failure of the different protection layers. And for sill determination, sill selection, we typically do not include the potential safety instrument of function in the analysis, because eventually you want to end up at a certain level of risk reduction that is required, which you then assign to that potential safety instrument of function. Alternatively, if you do include the safety instrument of function in your layer protection analysis, you should end up with no risk reduction requirement. But from a I don't know if I need a SIF perspective, you typically exclude the SIF from the analysis. So how does it work? The diagram is very straightforward. Initiating event, protection layer 1 is successful or not. If it's successful, then we stop. If it's unsuccessful, we go on to the second protection layer. If it's successful, we stop. If not, we go on to the third protection layer. If that one is successful, we stop. If not, then we have an accident occurring. Multiplication, logical ends is what applies to the quantification of this diagram. As an example, let's consider a pipe rupture where we have a release and fire from a brittle fracture of hydrocarbon line with a root cause of a process flow imbalance or a weather extreme. In this webinar, I'm only addressing the flow imbalance. There are a bunch of layer protections suggested for the flow imbalance. The operator responds to DCS flow alarms and stop the process. Other sensors will detect the imbalance and automatically close the control valve through the DCS to prevent the accident. The system has a separate independent PLC shutoff, which is our potential safety instrument of function. The pipe may not rupture even if exposed to low temperatures. or we have a source of ignition or control in the process area. So these are potential layers of protection. So one thing that we notice immediately, this independent PLC shutoff, the potential SIF, is something that we do not want to include in our LOPA diagram, because that is our potential safety instrument function. That's the one that we are determining the required risk reduction for. Also, operator response to the DCS flow alarm and other sensors will detect imbalance and automatically close the control valve through the DCS. Those two layers are not independent. They both use the DCS. So this is something where we need to take into consideration the failure of the DCS killing both layers at the same time. So our layer of protection analysis diagram for this particular case looks something like this. We have a process flow imbalance. The first protection layer is the operator response and the DCS taking action combined as one layer. Then the pipe may not rupture, and thirdly, there is no ignition. Those are the three layers of protection that were obtained from the description of the previous. Again, we combined operator response and DCS because they're not independent layers, and we excluded the independent PLC shutoff because that's our potential safety instrument function. The next step is that we quantify our layer of protection analysis diagram. Only need to calculate the frequency of the accident. That's what we're looking after. And how do we get that? Multiply initiating event frequency with the probability of failure of the independent protection layers. So if we assume the following input, process flow imbalance happens every 2.5 years, or we have 2.5 flow imbalances per year, I should say. Protection layer probability of failure on demand, the operator DCS combined of 0.05, pipe may not rupture, 0.33, and ignition source or contact 0.23 as the probability of failure on demand. Putting that into a diagram, quantifying it, and then calculating what is the final frequency of, in this case, a flow imbalance resulting into a fire outcome, 2.5 per year times 0.05 times 0.33 times 0.23, coming up with 0.0949 as the frequency at which we will have an accident, a fire, because of the flow imbalance. One thing to keep in mind here, and you may have seen this when I started the example actually has two, it's part of our training class. It has two aspects. Flow imbalance is an initiating event and a weather extreme. Those two would need to be combined because they both result in that pipe rupturing result. In this particular case, we only looked at one diagram. All right, the very important question here: where is a good source for generic data to get these figures? Very good question, because that question is always asked. Where do I get my data? There are some data books available, and things that pop in my head real quickly is if you look, for example, in the CCPS layer of protection analysis book, they have some example probability of failure probability of failures for different protection layers. The same actually is also true for 61511. If you go to part 3, keep in mind it's informative, there are some suggested protection layer probability of failures. There are some other industry books. I'm thinking of Loss Prevention by Lee's, a 3-volume book or 4-volume book. I forgot. I think it's 3. Could be 4. Volume book with which addresses these. And then we also have, for example, the CCPS has a guideline for safe automation of process industry with some sample information. And there are other data sources available. Majority of cases, people will actually use order of magnitude estimates for the probability failure for different protection layers, and basically say, okay, this protection layer will give me an order of magnitude risk reduction or 2 order of magnitude risk reductions. There is some judgment involved. Ideally, you have some plant history, for example, on your relief valves, indicating a certain probability of failure on those relief valves. And we will see this in just a bit with some example protection layers. But for a basic process control system, The typical probability of failure that you can claim is 0.1, but we'll see that in just a bit. So I hope that gives you some idea of data sources that are currently available. When it comes to layer protection analysis, there are rules, and rules with regard to what can we consider a protection layer. And these 4 need to be met for all protection layers. The protection layer needs to be specific, independent, dependable, and auditable. Specific means the protection layer must be specifically designed to be capable of preventing the consequences of the potential hazardous event. If we have a layer of protection that is not able to completely protect against the potential hazardous event, then we should be considering a layer of protection against this hazardous event. Layer of protections need to be independent. If they're not independent, then they could fail at the same time, so you need to combine them, as we did in our example. We need to take into consideration, in that case, that the DCS is basically the common factor between 2 layers, and we combine them in one, as one layer, because if the DCS fails, both of my layers fail. Dependable, we must be able to act dependently when the situation occurs. So basically the layer needs to be always there. And then lastly, we must be able to test the layer, which is going to be a little bit difficult, for example, on a rupture disk, but you could argue that that manufacturer tests 1 out of a batch, or for your relief valves, it's a little bit easier. They typically do, or you're typically required to do a pop test every 3 years, at least here in the U.S. as part of a ASME standard. So you have that aspect at least taken into consideration. All right. Next couple of slides are some examples of typical protection layers, and I also hope that that these will help you in giving you some feeling as to where do I get my data for these protection layers. The first protection layer that people like to look at is the basic process control system. I have a control function that protects against this. There are some requirements or conditions that need to be met before you can consider basic process control system a layer of protection. And the first one is that the basic process control system and the safety instrument system are physically separate devices, including sensors, logic solvers, and final element. If they're not independent, then one of the requirements of our layers of protection, independence, is not met. And you would need to consider the 2 as one layer. But if the BPCS and the SIS are physically separate, and the failure of the BPCS is not responsible for initiating the unwanted event, you do not want to take credit for the BPCS as a layer of protection if the BPCS is the initiating event. It's not going to protect against itself. And then lastly, the BPCS has the proper sensors and actuators available to perform a function similar to the one that is performed by the safety instrumented system. If you meet these 3 requirements, then you can claim a probability of failure on the mount for this layer of protection of 0.1. And what is that 0.1 based on? It's by definition, as you can see on the slide, it's based on a statement in 615.08 and 615.11 that if a programmable electronic system that is not developed per the 615.08 standard is used as a protection layer, then the maximum risk reduction that you can claim is an order of magnitude, basically still 0. If you use a safety certified PLC to perform your control, then it's a different story. You could go with a probability of failure that is less than the 0.1, but again, that's when you have a safety PLC that is developed per 615.08. Another question here is who normally facilitates layer protection analysis meeting? Is it normally done by the end user? Can it be done by the design engineer, or is it a third party? Arguably, the answer to this question is yes. It all depends on how you structure your project, and that is part of your functional safety management that you need to implement as part of 61511 compliance. But you can have, well, in the end, it's the end user who is the overall responsible party with regard to 61511 compliance. The end user could have a team of people that is educated in this and that can facilitate the layer of protection analysis. You could also hire a third-party consulting firm. Exid is happy to do this for you and have those people do it. Or you could have maybe an engineering company that has some experience with the layer of protection analysis and have them do it as well. The key is, and this applies to everything that you do with regard to IEC 61511, that the person or persons that are performing a specific task as part of your functional safety lifecycle are competent in those tasks. So if you have a design engineer who is very good in coming up with a conceptual design of a safety instrumented function, given that he has the input, I need a pressure protection, this valve needs, or the output of this tank needs to be stopped, and we need an integrity level of XYZ. If he's very good at that, but he has never done a layer of protection analysis, then that would not be an adequate person to conduct a layer protection analysis. It's typically, the majority of times that I get involved is when a third party is included, but obviously I am the third party in that case. But I know of some customers that use our software that obviously they will be conducting these analyses themselves. So it depends on who within the 61511 compliant process is assigned to do this task. And eventual responsibility is by the end user to find someone who is capable or competent enough to do this. So that is the BPCS protection layer. Let's go through some other protection layers. Operator response. Quite often, you will hear comments like, hey, we have an operator can do this. Well, there are a couple of requirements to the operator. Number one, the operator needs to be always present. Dependable was the requirement, of one of the 4 requirements of a protection layer. The operator needs to have an indication of the problem. He needs to have time to act. He needs to be trained in the proper response. And if you meet those 4 requirements, then okay, you can arguably claim a 0.1 probability of failure on demand for the operator. If the operator doesn't have enough time, and the rest is met, but he doesn't have enough time to react, then simply probability of failure is equal to 1. You could go lower than 0.1 probability of failure if you do a detailed human reliability analysis. In the process industry, I would advise against that. We've seen it quite a bit in nuclear industry, where operators are trained every month in a complete mock-up of a control room looking identical up to the coffee pot and the level in the coffee pot to the normal control room, and where they're subjected to all possible deviations. I can see that you can claim anything lower, lower probability of failure than the standard 0.1 in a situation like that. But also keep in mind that many of the people that are involved in these type of analyses, the layer protection analysis or the PHAs, sometimes do not include the actual operator, maybe a supervisor who says, well, we have an operator for that. But if you talk to the actual operator, he may say, well, it's probably better not to count on me because I have all these tasks to do, and I may be on my round, and I need to react within 30 minutes, but my round is an hour. That is something to take into consideration as well. One question here: how can you claim less than 0.1 for the use of a safety PLC if the I/O is not rated? in my assumption of, or in my statement of claiming less than 0.1 for a safety function, I should say safety function versus a control function, and my assumption there was that the entire loop was a safety and semantic function. So it's not just the controller itself. I may have hinted that I was talking about the controller itself. I talked about an entire safety and semantic function versus a control function. Another protection layer, use factor. If the hazard is not always present, basically your time at risk divided by total time. If you have a batch process, this is something that gets taken into consideration quite a bit. Keep in mind that if you assume you're initiating event frequencies based on the normal batch operation, then you have taken this use time already into consideration. If you have initiating event frequencies that are based on continuous operation, then this is something that would apply. Mechanical integrity of a vessel. If a vessel is designed to withstand the pressure and temperature generated as a result of the initiating event, then you can claim that as a layer of protection. Some organizations will even go to claiming the cheese is full, there are no holes in the cheese, probability of failure is 0. That is quite optimistic from a, everything can fail perspective. I don't believe in the absolutes. Things are not possible and things are always possible. There is something in the middle. So the more conservative organization, PFD of 1 year of random failure, that would be more appropriate. We have an example here where data from ARETA was obtained for significant leakage, and we basically took the 1 year of random failure off the significant leakage, and we ended up with almost 3 orders of magnitude risk reduction. And in the majority of cases, if you end up with 3 orders of magnitude risk reduction, your required risk reduction is very low. So if there is any required risk reduction left at all. So it's probably better to go with the conservative assumption that, yes, everything can fail, but it's very unlikely that it fails. Account for it rather than say this will never be a problem. All right, we have another question here. Who and what will determine what is requiring LOPA? I'm assuming there that the question is related to why can't we just simply stick to a risk graph approach or a hazard matrix approach? Why do we have to go into this level of detail? Who and what is the end user? It all depends on your corporate philosophy. There are people that stick to the risk graph, that stick to a hazard matrix, and do their SIL selection with that. With these methods that are qualitative, you have to categorize the different frequencies and consequences in broader categories. And one of the, I don't want to call it a risk, but one of the aspects of that is that you tend to end up with conservative estimates and consequently higher, relatively high risk reduction requirements. Those requirements may be warranted even if you go into more detail, but in general, the more detailed your analysis will be, the more accurate your resulting answer will be, the less, arguably less conservative you are in your estimates. So what we typically see is an initial SIL selection with a risk graph or a hazard matrix, resulting in a bunch of SIL 0, SIL 1, 2, and 3, and then an additional more detailed SIL selection with the SIL 2s and SIL 3s to make sure that these are actually SIL 2s and SIL 3s. And why is it important for many end users to do that? Implementing a SIL 1 safety function is I'd say relatively cheap. Majority of cases, that just means a single transmitter, a single valve. If we talk about the SIL 2 or SIL 3 safety function, then you probably end up with redundant inputs, redundant outputs, and that could become very costly, not just from an initial purchase perspective, but also from a lifecycle cost perspective. So that is the reason why people typically want to put in a little bit more emphasis on the higher level of risk is, do we really need a silt-free safety function, or do we already have a good design in place? Maybe we have a pressure relief valve that will help protecting against the overpressure event, but that typically not necessarily included in that initial risk ranking in a risk gravel hazard matrix. So let's see what other layer of protections we have. Relief valves, rupture disc, I already mentioned them a couple of times. Probability of failure data for these things can be found in databases. Mentioned a couple. External risk reduction layers, water spray curtains, dual wall piping, enclosures with scrubbing. We need to make sure that these external risk reductions are capable of completely eliminating the hazard. If they're not, then arguably the larger consequence is now a smaller consequence, and we need to continue our analysis with the smaller consequence. Let's see, ignition probabilities, and these come from textbooks as well. 0.3 for flammable gases, 0.12, 0.3 for volatile liquids, and less than 0.1 for heavy liquids. Keeping in mind, plants are designed to limit sources of ignition. The function of the probability is a function of the release size and release materials, and hazardous area classification is important to take this into consideration. Very rarely people use something as an explosion probability, probability that explosion will occur given that ignition has occurred. Typically, we assume that if there is ignition, there is an explosion. But there are maybe a handful of scenarios where you can consider it. Occupancy, the time that the area is occupied versus the total time. Let's say I have an unmanned platform, and 1 week a year, 1/52 in that case. I send a maintenance crew out there, and if I'm concerned with the consequence of hurting a human being, and I've assumed in my consequence classification that the platform is always occupied, then I can take this occupancy factor into consideration. But the key is that you have assumed continuous, normal, fully occupied situation from your consequence perspective, and then you take the credit in your occupancy factor, in the occupancy layer protection. So those are some layers of protection. One thing I think that we didn't list are dikes. Sometimes personal protective equipment is considered as well. Specific procedures could be considered if there are different people executing those different procedures, and so on. We have at Exid, we have a software package that is called Excelencia that covers the life cycle. The base package comes with a select tool, a SIF SRS, and a silver tool that relate to the risk analysis, SIL selection, the safety requirement specification, and the SIL verification, respectively. We have plugins like a PHA import that I talked about last week a little bit, a proof test generator that will help you determine what the steps should be to keep your equipment, keep the safety integrity of your equipment. And we also have a safety requirement specification C&E plugin that basically splits the requirement specification up into two separate documents: a process SRS and a design SRS. The process SRS documents all the requirements from the risk analysis and SIL selection. So, for example, the hazard, high pressure in the vessel, I need to detect pressure, I need to stop flow to this vessel, and the integrity level needs to be SIL 2. All that is documented in the process SRS. I do my SIL verification, my conceptual design, and then I end up with a document that I provide to my detailed design people that that could say, for example, well, I need 1 out of 2 transmitters, I need 1 out of 2 final elements, or I need 1 final element with partial stroke testing. So that would be more detailed information that I then hand off to the detailed engineering. So these things together are our Excelencia software at this point. And in our select portion of the base package, we can deal with independent protection layers. You can put in a description for a protection layer. You can put in the probability of failure of that protection layer as of course, if the default value is 1, it always fails. Or you can specify it in terms of risk reduction factor. And you can consider a protection layer effective for all possible risk receptors, personnel, environment, asset, and in our case we have one that is custom defined by the user. Could be society, could be business liability, whatever you want. So you can define if a protection layer has different level of effectiveness for the different risk receptors. So you could, for example, consider a pressure relief valve, 2 atmosphere, would protect personnel somewhat, because rather than having a big rupture of a vessel, you have a more localized eruption. It would protect the asset in that the vessel will not rupture, but you could argue that, hey, the environment is still damaged. This protection layer is not adequate for my environmental protection. So you could say, let's say a 0.1 for personnel, probability of failure, a 1 for environment, and maybe a 0.01 for assets. So you can consider different protection layer effectiveness for the different risk receptors. You can implement the laser protection as part of your risk graph, as part of your hazard matrix scenario, where you do your initial classification and then basically specify layers of protection, and then using the layers of protection you end up with a target safety integrity level. We also have the complete LOPA. Let's call it the complete LOPA, where you specify an initiating event frequency. That happens somewhere in the middle of your screen here, initiating event. You specify the frequency. You specify if there's an enabling condition. That's typically the use factor that will be considered there. And then you can add the layers of protection, and it will calculate the frequency of the unmitigated event. You can specify more than 1 initiating event if necessary. You get the sum of all unmitigated event frequencies. That is compared to a tolerable frequency. The tolerable frequency is based on your severity level selection. So in this case, we talked about a single fatality apparently. You compare your unmitigated event frequency to your tolerable frequency, and from that you determine how much risk reduction you need. In this particular case, if you look at the bottom, this is just an example, we ended up with a required risk reduction of 60, and it was specified that we needed a SIL2 safety function. Alternatively, you could have specified a SIL1 with a minimum risk reduction factor of 60, but that goes more into the SIL selection aspects. The layer of protections, basically the same for the different selection methods. So this is how we have engineering tools that can support your layer of protection analysis methodology, and as you see, you can implement it from a pure initiating event with the different layers of cheese, so to say, perspective, or you can also put the layers of protection and embed those in your risk graph and hazard matrix analyses. For those of you who are interested in the Excelencia software, we have an online product that runs on our server. You can basically log in through a web browser. We have a standalone product which you install on your local PC. You get a USB dongle to use that. We have a site license where there's one license key for 5, 10, 25 people. Or we have a server product which is installed on a company's server. All these tools are identical. They have the same functionality, the same compiled object, etc. We do offer training classes, and for those of you who are interested, we are going to conduct the Excelencia Users Group in Houston, Texas, May 19th through 21st this year. It's going to be our first users group. You could argue that the economic climate is not ideal, but oh well, it's going to be a very nice event. The first day, which is going to be Tuesday, we will have a training class where we will go over our Excelencia training material. The second and third day, the Wednesday and Thursday, we will have the actual users group. We are going to have some user presentations, and we will also talk about the overall overview of the software, the different plugins that we have. There's going to be a panel discussion where if anybody's listening who is a former AIM Sales Suite customer, you may know that Exid bought the AIM company, and we therefore own the Sales Suite software. We are working on integration of that with the Excelencia software, and we're going to talk about that as well during this users group. So mark your calendars and look at our Excelencia.com website. Go to About Users Group for more information. Some additional resources. We have books. We recently released a book, Final Elements and the IEC 61508, 61511 Functional Safety Standard. Those of you who are familiar with the original concepts of 61508, 61511, the 61508 is called the Functional Safety for Electrical, Electronic, Programmable Electronic System. Then as people started to work with it, realized that safety is only as strong as its weakest link. You need to include the final element as well. So final elements were included as part of that, but mechanical safety is sometimes a little bit different than electronic safety, and this book will definitely provide some guidelines on that. For those of you who are attending the Excelencia user group, this is one of your gifts for attending. You will receive a free copy of the Final Element book there. So in addition, we provide training, consulting, certification, etc. Any questions? Please use the Q&A on the top of your screen. I'll try to answer those questions. For those of you who don't have any questions and are about to sign off, thank you for attending this webinar. I hope it was informative enough. If you have any questions later on, you can always email info@exida.com. And as I mentioned before, this webinar is going to be made available as a download, or not necessarily download. You can listen to it online, I think, this afternoon. So if you want to listen to some of the things we talked about, again, you can do that this afternoon. And also the other webinars are made available online as well. So if you missed one, you can always check back on that. Okay, I have a question here. Can you clarify the exact title of the CCPS LOPA book that you talked about? To the best of my knowledge, it's simply called Layer of Protection Analysis. Let me try and look it up real quickly. Let's see. Yep, I just found it. Actually, just go to Amazon.com or any other of the online outlets, and you'll probably be able to find it. But it's called Layer of Protection Analysis, Simplified Process Risk Assessment. So that is the official title of the book. It's authored by the CCPS. And let's see if I can find some more info on this. Trying to find an ISBN number, but basically Layer of Protection Analysis, Simplified Process Risk Assessment. It's authored by the CCPS, Center for Chemical Process Safety, which is part of the AICHE, the American Institute for Chemical Engineers. It doesn't seem that there are any other questions. I'll hang around for just a little bit longer. I'll start to mute my microphone, but I will stop the recording at this point.